Alright, let's begin. We are going to pick up with chapter 13.
What happened with you?
And I'll no, we're skip chapter. So chapter 13 and yeah, we'll probably review it then. I'll maybe go to like 7 or something.
Okay.
Do the rest of it.
Yay.
Wait, what?
So chapter 13 is pretty short.
No, he's going to go about
Chapter 13 is not that short,
And then he's going to
actually.
review for
Oh,
test.
so we're going to break it down in 2 days?
I don't think we'll finish it.
Okay.
Okay, so we did that whole thing where we did that table, the probability distribution, finding the y values. Okay, let's talk about the averages. From probability distributions. The average here is kind of talking about the mean average. Definition. The mean, or you might see this phrase if you're looking at the finals or homework. It's called expected value. Of a discrete random variable x with probability distribution. So say you have a random variable and you know its probability distribution. So it starts with x and p of x, and here's an x1 value, x2 value, dot dot dot, all the way to xn value. And then this is a probability of that, probability of this one, dot dot dot, probability of that one. So if I know a random variable and I know its probability distribution, I can actually talk about the mean or the expected value of this, right? And is given, the mean, this probably is given by, did I give you the summation notation?
No.
So it's called mu x or ex, right? The e here stands for expected value. And this is defined to be the sum of xi times pi over all n's, i.e. the expected value of my variable x is given by x1 times p1 plus x2 times p2 all the way down to xn times p. Right? So I take this times that plus this times that plus this times that all the way down to the end, and this gives us the average of what you'd expect. Right, so this outcome will happen with this probability, or this outcome will happen with that probability, or this all the way down. Right, and that's on the average of all these is sort of what you expect. The probability you're already dividing by a total, so that's where the mean average comes in. It's a number of things out of the total. Okay, that's pretty much the definition.
So there's no division?
No, the probability already has the built-in division. Remember, in the probability you're already dividing by that total. Right? So when you have a probability distribution, you just multiply the event by the probability, you add them all up together, and that gives you the average. Okay. So
And
let's
X
do it
is
again.
just a random event.
X is a discrete random variable. So it's a variable that can take on only specific values according to some probability. Okay, so let's do an example here. Consider the game of tossing a coin and earning money in the following way. Tossing a die, not a coin. that wouldn't be very interesting. Okay. So here's the thing. If it lands on 6, you get $3. If it lands on 3, you get nothing. If it lands on 1, 2, or 5, you lose $1. If it lands on 4, you gain $1. Now on top of that, to actually play the game, you actually have to buy into it by $1 to play the game. Not 100, because that would be crazy.
This is similar to a pirate.
The buy-in to play the game is $1. Right, so you paid the dollar, and you can actually play this game, and you can actually earn money in that according to that criteria. So here's the question: how much money do you expect to win on average?
Depends on how long you play.
So you have to buy $1. to
Keyword on average. On average per play. Follow-up question: is the game worth playing? I mean, it costs only $1 to play, and look, oh, you can land on this and you can get $3. Right? You can pay $1 and you get $3 back. Triple your money. Is the game worth playing?
Is it possible for the answer to be like it's half, like it's split in half, like it's neither good nor bad?
That would.
Then it's a waste of time.
Well, we'll see from the numbers what the numbers will tell us.
It's bad.
Okay. So, what do you think?
It's bad.
You have to find out how many ways you could gain and how many ways you could lose, or just learn one. And
So one thing we'd want to define here is define a random variable to actually measure our winnings, right? So x equals the expected win per possible net gain per play, right? What are the possible values of x?
could be 6. Right. Could be like 6 or 4.
How do you mean 6? You can't get to a 6.
Net gain.
Well, what are our options?
3 are possible net gains. No,
Remember,
net
you pay
gains.
$1 to play, right?
Oh,
So if you pay $1 and then you win $3,
$2.
that means your net gain will be $2. So 2 is a possible value. We're probably going backwards, but whatever. What's another possible value?
Wait, no, let's go forward.
0.
Yeah.
Let's start with the minimum. Worst case scenario is what?
0.
You lose another $1, right?
Oh.
If you land on a 1, 2, or 5, they take another $1 from you, right? So you'll be down. You'll be in the hole by how much?
-2.
-2, because you already paid $1 to play, and then you're going to lose another $1, so you can lose $2. That's one possibility, right? That takes care of this one. You can win nothing, right? In which case, what's your net gain?
1.
-1.
-1, because you're paid $1 to play, right?
Oh, it's in U.
And then 0.
You can actually gain $1, right?
Zero.
But you paid $1 to play, you gain $1 back. You netted nothing, so that's 0 is one possibility. Or you can pay $1 and gain 3, right?
2.
Which means I net $2 profit, right? So these are the possible values for my X, right? How much I expect to win at the end of this game. Okay, so now let's talk about P of X. What's the probability of P of X? What's the probability of actually losing $2 at the end of the day?
Is it
3 out of 6.
When does this happen?
1, 2, and 5.
1, 2, and 5. What's the probability of getting a 1 or a 2 or a 5? When I
3
roll
out of
die?
6.
3 out of 6, right? Because there's 1 out of 6 chance on each of those. You add them all up together because they're mutually exclusive. So the OR translates to plus, and you just add them all. 1, 6 plus 1, 6 plus 1, 6. What's the probability that I get this?
1 out of 6.
1 out of 6. This?
1 over 6.
1 out of 6. Right? So this is my probability distribution. So now if I ask, on average, how much money do you expect to win? So if I ask you about my expected value, what would that be?
You have to multiply -2 times
This times this, plus
its
this times that, plus
possibility
this
and
times that,
that.
plus that times that, right? So you could earn -$2. The chances of that happening is 3 out of 6. Or you can lose $1, and the chances of that happening is 1 out of 6. Or you can win nothing, the chance of that happening is 1 out of 6. Or you could gain $2, and the chances of that happening is 1 out of 6. So at the end of the day, what is that value?
-1.
Yeah, so this is a -1, minus 1/6, plus 1/3, right? So that would give me -6 over 6, minus 1 over 6, plus 2 over 6, which gives me what?
-5 out of 6.
-5 out of 6. Yeah.
Can you go over how you got -2 again? I know we started with you paying $1, so your net automatically becomes
Yeah,
-1.
just to start the game, you're already at -1.
Okay.
So then if you're at -1, and then you lose 1, now you're at -2.
Oh, that's same.
Right? Like our base was -1 to even
Yeah.
start playing, right? Because you had to, the buy-in was $1, right? So you already started at -1 before even playing. Now, given that, if you lose 1, you're now in -2. If you don't gain anything, you're stay at -1. If you gain back 1, you get 0. If you gain 3, you're back at 2. That's your net. We're looking at the net gain here. And that is the net gain per play. This is the average. So what this is, that is actually the average that you'd expect to win. -5/6 is the average expected net gain per play. Is it worth playing? No, because you're losing money, right? This basically says if I play 6 times, I'm going to lose $5, right? On average, for every time I play, I'm losing 5 out of $6, right? So if I play 6 times, I lose $5. If I play 12 times, I lose $10, and so on and so forth, right? So based on the probabilities, this is not a smart game to play. By the way, as I mentioned how, this math kind of controls your life, expected value is probably something that insurance companies would use to figure out how much to charge you, right? So they know on average, if they gain a certain amount of money by you paying an insurance premium, what is the probability that you wreck your car, right? And they'll lose a certain amount of money, right? And then they add up all these expected values, and they sort of do it in such a way that the number over here is a number they like, profit, right? You do it so that you get something positive. So then if you're a 24-year-old male with a sports car, red Ferrari, you have to make the positive really big to make up this number really nice. So they're going to charge you a higher insurance, right? So this is the kind of things they're looking for. The chances of you actually crashing that red Ferrari, given that you're a young male with first-time driver's license. So these are things like how much you expect to win. So you go through a situation and you sort of map out all your possible wins and losses and the probabilities of each, and on average, how much you're expected to get would be done by this computation. So that's something that you need to know. Very nice. It's also a very important topic. Expected value is a big thing, and it's actually the same as the mean for a random variable. We can also do things like standard deviation. A discrete random variable. Is given by sigma is the symbol, but we put x here because my random variable is x. x1 minus mu squared p1 plus x2 minus mu squared times p2 xn minus mu squared times p3 pn. So just remember, your Pn is sort of like that whole division by n minus 1 here. So the idea is once you have those probabilities, you don't have to worry about division. So it's the same as x minus x bar and so on and so forth squared all over n minus 1. And that accounts for the probability. So that will be your actual standard deviation.
Wait a second. P, you said you're subtracting and then multiplying by P1. By the probability.
Yeah, each guy minus the mean, you square it, and then you multiply by the probability of that outcome. Multiply by the probability of this outcome, multiply by the probability of this outcome.
Is mu going to be given?
No, mu is this.
Oh.
Mu is the expected value.
Gotcha.
So if it's not given, you can figure it out.
Okay.
The mean is the expected value. Those are synonyms. So whenever you're in the probability section, they say expected value. They're talking about mean, and this is how you compute it. Also, remember that the variance is just the square of the standard deviation. So you can do the variance of x. It's just the standard deviation squared. That's nothing different about that. And now we're going to go back to counting. We're going to want to describe some more complex situations that we've dealt with before. We're going to need some new machinery. Yeah, expected value is extremely important. They use that to set up a lot of things. How much to charge you for your mortgage, insurance, health insurance. Basically, this is the kind of stuff that actuaries will do. They assess the risk and they try to finesse it so that their company makes money. Okay. So we're going to want to be able to count more complex situations. So we're going to talk about combinations and permutations. So let's do that. Definition. For a non-negative integer n, I'm going to denote n factorial. N factorial, which, by the way, the notation for n factorial is n with emphasis. you actually read that n factorial. You see that I say n factorial. Okay. So for a non-negative integer, n factorial denoted this is the product of all integers from 1 up to n. Unless n equals 0, then then 0 factorial is equal to 1 by convention. i.e., n factorial just means 1 times 2 times 3 times, go all the way up to n. Multiply all these numbers. An example is 3 factorial, that's just 1 times 2 times 3, which is 6. Or I can say 5 factorial, it's 1 times 2 times 3 times 4 times 5, it's 120, etc. Right? This is called a factorial. So leave up next. Now, factorials are used all over math, but how we're going to use it is with this interpretation. N factorial gives, does anyone know, like a concrete interpretation of this? What n factorial gives you?
I was going to ask, but if you want to go backwards.
It's the number of possible arrangements of n objects. That is called n factorial. So for example, 2 factorial equals 2. This is the number of ways to arrange 2 objects. Right? So if I have 2 objects, A1 and A2, I can either do A1, A2, or I can do A2, A1. There are 2 ways to make an arrangement of 2 objects. Right? If I have 3 objects, three factorial equals 6. This is the number of ways to arrange 3 objects. That means if I have 3 objects like A1, A2, A3, I can arrange them in that order, or I can arrange A1, A3, A2, or I can do A2, A1, A3, or I can do A2, A3, A1, or I can do A3, A1, A2, or I can do A3, A2, A1, right? There'll be 6 ways that I can arrange objects in a different order, right? So if I want to know how many ways can I arrange 3 objects in different orders, there are 6 ways, 3 factorial. How many ways can I arrange 5 objects? Turns out 120. If I start doing 5 objects, the number of ways I can put them in different orders, there are 120 ways to do that, right? It grows really fast. So you can see why we want an efficient way to count this, because they can get really big, and it turns out that this is the best way to count it. It actually uses the multiplication rule. I can probably mention that. By the way, this uses the multiplication rule. Right? If you have 3 objects, there are 3 possible slots, right? To put something in the first slot, there are 3 choices, right? But once you put someone here, there are only 2 choices remaining for this one. And then once you put one there, there's only 1 choice remaining for this one. Multiplication rule says you take 3 times 2 times 1. Right? If you had 5 objects, then there are 5 choices for this position, 4 choices remaining for that position, and so on and so forth. To kick the camera. It was you. Make sure it's lined up. we're still good. Cyanide, you haven't foiled us yet. I saw it. Somehow, I don't know how you did it. Right? So it's using the multiplication rule. So n factorial actually gives us a number of ways to arrange n objects, right? So arrangements are going to be very important. Here's another thing that I want. I think combinations was what I tell you about next. Okay, yeah, the combination is another definition. It's called a combination. A combination. There are many different notations. It could be NCR, or you could put C and R, or you could put NR, just let brackets like that. Is the number of ways to choose R objects from N objects in no particular order. So like here, the kind of arrangement's order matters, but if you don't care about the order, you just want to pick some elements out of a bat, a combination is what you want to use. For this reason, I recommend that you memorize it this way, in which mathematicians, when you're talking about it in English, they'll normally say it this way. NCR is red, and choose R. Right? So you think of n objects, and you're choosing R objects out of those n objects. It is defined by this formula. NCR equals NR equals n factorial over R factorial and minus R factorial. That's that definition. By the way, it's a built-in function on your, if you have a TI 80, blah, blah, blah.
TI 84.
Yeah, even 83, right? So,
Yeah, even 83.
yeah, even the 83, you're like way,
You're still in 2008.
it's like way in the stoning. Like if you still have like a flip phone and you have a TI 83. On TI, what you would do here is you would enter to find NCR. What you would do is you type the integer n, whatever number that is. Then you would press
Math,
math.
and then go to PRB.
So you press, so I'd enter a number, let's say like 5. So let's example, 5C3, right? How many ways can I choose 3 objects out of 5 objects, right? So you'd enter NCR math, you would go 5 math. You'd have to press the arrow to go over to probability, PRB, and it will be option 3.
And TI 84 is 4.
It's option 3, and it will actually say this. You'll see NCR, right? This is a TI 83, it's actually option 3. It might be some other option. You'll notice that option 4 is factorial. So if you want to put in a factorial in general, you have that. And then after you choose that option 3, you enter the other integer, R. And then you press equal. Right? So if I wanted to do this, I would enter 5, math, go to probability, choose option 3, then enter the number 3, then press equal. And the answer would be 10. So if I have 5 objects and I'm randomly choosing 3 objects out of it, there are 10 ways I can do that. I can choose 10 different sets of size 3 out of a set of size 5.
So you have 1, 2, 3, 4, 5, and you want in a pattern of 3.
I want to pick one. So it's like I have a list of things, A1, A2, A3, A4, A5, and I want to pick 3 things out of this list.
Okay.
So there are 10 ways I can do it. I can pick A1, A2, A3, or I could pick A1, A3, A5, or I can pick A2, A3, A4, or I can pick blah, 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 right? All of those possible ways I can do, in which the order doesn't matter. If I rearrange them, I don't care. There are 10 ways I'd be able to do that.
Are we gonna use NPR ever?
Yeah, NPR.
What is that?
That's permutations. That's kind of the same thing here, but your order does matter. Right? So there are cases where it's going to be something like, I might say, okay, we have 10 people and I want to create a committee of 4 people, right? How many possible committees are there, right? Like if I have 5 people and I want to create a committee of 3 people, how many possible committees are there? Well, it's 5 choose 3. There are 10 possible committees. But if I said, okay, I want to create a committee where there's actually ranks. There's a president, a vice president, and a treasurer. Then the order would matter, right? There's someone who's going to be in first position, in second position, in third position. In that case, you choose 5P, right? So when order matters, you use the P. When order does not matter, you use the C.
A higher number if you use the P.
Huh?
A higher number if you use the P. 60 in P.
Yeah. There's a form for that. I don't think we use that directly, but we can do that. Okay. What else do I want to tell you?
I believe it took me this long to learn how to use that damn calculator.
Early than never. Okay, let's actually do an example.
Imagine you break it or like lose it.
No. It's just
Yeah.
like 8 for 8.
Aww.
Actually, use 10. There are 10 people.
AP's kept it for so long. I've never had anything that long. Not even pets.
Someone's afraid of commitment. To be on a committee. If the committee must have 4 members, how many possible committees are there? How many possible committees can be made? So here I'm not given a rank, I'm just randomly choosing 4 people out of 10 people. So the answer
10.
is you take 10, choose 4. Right? That's 10, choose 4. Okay, try to compute that in your calculator.
210.
210 should be the answer that you get. If you don't get 210, you're missing something. And if you don't have like a graphing calculator, then you just enter this formula directly. So you'll actually enter 10 factorial divided by 4 factorial and 6 factorial. And make sure in your calculator you put this in parentheses. So you put 10 factorial, the division sign, open parentheses, this times that, close parentheses. And you should also get this. I didn't write down this example, but I might as well tell you guys about this. What if ranks existed, i.e. there is a first, second, third, and fourth position. Then what you can do is you can, one of the reasons why I didn't really directly tell you about NPR is because you can sort of use the multiplication rule. The idea is for the first position, the second position, and the third position, and fourth position, there are 10 choices for the guy in first position, right? But once you put someone in first, you only have 9 to choose from. So there are 9 options for the person in the second position, 8 options here, 7 options here. So if you multiply those guys, you get what number? 5,040? Right, now that number in your calculator would
Wait,
be...
we're still doing, I used 10.
Yeah, 5,040, yeah.
Yeah, so this is, in your calculator, that would be NPR. So this is the guy you use when order matters, like if there's a first and a second and a third. If order is random and I don't care about order, I use the C. Right? Technically, you don't really need to worry about this. Like I said, in this situation, using the multiplication rule idea, you can get to the answer anyway. Okay, so with that in mind, we can talk about a very important discrete random variable. Very important because it happens all the time. It's very ubiquitous. There are many situations where this guy fits a situation. It's called the binomial random variable. Again, the word bi means two. So this is kind of talking about a situation where you only have two possible outcomes. So, let x be a random variable. How do you know when you have a binomial one? You need two possible outcomes, they're all independent, and you're doing something repeatedly n times. How did I phrase it? Differently. Let me start out with the list. Suppose you have these conditions. And you'll be surprised how often you actually have these conditions. 1. Repeat an experiment, an event n times. 2. There are only two possible outcomes, right? Has to be 2. 3, each outcome is independent of others. Right? So the two outcomes, you classify them as success or failure. Right? Success is whatever we're looking for to happen. Right? Failure just means that doesn't happen. Okay. Now I'm going to define a random variable. Let x equals the number of successes for these n experiments. Then x is a binomial random variable. And now I'm going to give you the equation, super important. The probability of x equals k is n choose k, p to the k, q to the n minus k. Where n equals number of times you're repeating the experiment. K equals number of successes, right? Meaning the number of times what you're actually looking for it to happen happens. P is the probability of having a success, where the chances that on any one experiment you get success. Q, which is 1 minus P, is the probability of failure.
Well, I thought x was the number of success.
Yeah, but x is a variable, remember. X can take on multiple values usually. K, I'm talking about some specific value. So what's the probability that x is equal to a specific number, right? So they can actually, what's the probability that we'll get 5 successes here, right? Then K is your number of successes. So also knowing this is really important, so put a star on that. The 3 situations that must happen for it to be binomial, you have to know those, right? So you're doing the same thing over and over a certain number of times, n times. There are only 2 possible outcomes, and each outcome is independent. You have to know that. Because you're gonna, when we're talking about these, it's gonna be a word problem, and I'm not gonna tell you it's binomial. You're just gonna have to read it and figure out, oh, it's binomial, because only 2 things can happen, they're all independent. And we're repeating the same thing.
This isn't going to be on the test on Wednesday.
No.
No.
Okay, just want to make sure.
Bonus, right, maybe? The bonus question?
Maybe.
Ooh. I think he's going to ask us to say that formula for the bonus.
Moreover, we have the following. The mean of x is actually n times p. The standard deviation of x is the radical of n times p times q. And this just comes from plugging into that formula that I gave you guys earlier. If I plug into that formula and I simplify everything, these are what you come up with. I guess that we don't really talk about this very much, but the variance would just be sigma squared, which is just npq. But these are the 2 important ones to know. So know the 3 conditions that make something binomial, know the formula for the probability of a certain number of successes, and know what the mean and standard deviation of a binomial random variable are. So this is for x binomial. Well, I would give an example, but it's 7, so you can stop there and do a review. But yeah, binomials are really important, because a lot of times we really want to know whether something will happen or not. Right? Is it going to rain tomorrow? There are only 2 options, yes or no. Right? There are tons of things going to be yes or no. That thing where we're in the blood bank, right? Will the guy get the blood he needs if 10 people randomly walk in? There were 2 options, yes or no. right? A lot of things are yes or no answers. And usually when you have a yes or no answer, something might happen or it just might not. A binomial is where you're going to go. So that's sort of, and there are a lot of things that you phrase that way, where you just want to know yes or no. It's either this or it's that. There are only two possible outcomes. You get what you want or you don't. Many things are phrased in that way. And when something is phrased in that way, where you're repeating the same process over and over, and there are only two possibilities, and they're all independent, that's binomial. So we never talked about binomial when we were doing that blood example, but it was binomial because each person's blood type is independent, right? First guy walks in, what his blood type is had nothing to do with the second guy's blood type, right? Now you're repeating an experiment, right? You're testing their blood to see if they're the right blood type to give the guy. So the person A walks in, you test his blood, it's either the right blood type or it's not, right? The second person walks in, you test his blood, it's either the right one or it's not. Third person walks in, you test his blood, it's either the right one or it's not. You're doing exactly the same thing over and over and over again, and there are only two possibilities. It's either the blood type you need or it's not, right? So that was actually a binomial random variable, right? So, and that kind of situation is something you have to know. Like when you read that problem, you should have recognized, or you should be able to recognize now, that it's a binomial random variable. And I can get to ask you a lot more complicated questions now that you have this formula, but we'll see that next time. Questions on the review problems? No? We have 40 minutes, so make it good. Can I get rid of everything?
Yeah. Yes.
Okay, spring 09, number 5. What did that say? Spring 2009, 5. A study of weight versus height of adult males gave the regression line formula of y equals minus 180 plus 5.2x. So y is weight in pounds, x is height in inches. We know that Sx equals 2.5, Sy equals 18. Okay. So we're given that regression line. X represents the height in inches, Y represents the weight in pounds, and we want to know A, find R. How do you find R?
Well, you have to write down the formula to find the slope, which is b hat.
Right, B hat is
R times the deviation of y divided by summation, right? Then you have
the B hat is
5.2.
the slope, right? So you know that B is the slope, so this means you have 5.2 is equal to R times Sy over
Which is 18 divided by 2.5.
Yeah. So then you have R is equal to 5.2 times 2.5 over 18. 0.74. So moderately strong positive correlation here. B, what is the average weight? B, average weight for
68 inches.
68-inch tall man.
Jhevon,
Yeah.
is this 0.74 or 0.72?
It's 0.722.
Yeah, it's 0.
I don't know. I didn't get that number. Okay, what's the average weight?
It's
Well, just y. Plug it in here.
173.6
So
inches.
5.2 times 68. So this would be, you said 173.6
3.6 inches.
pounds.
Oh, right.
Right, y is the weight. Yeah, so the regression line relates your weight in pounds to your height in inches. So that's going to be that. Yeah, so C, I never really gave you anything like this. For C.
Aren't you supposed to take
Well, you did tell us the 68, 90, something, 89.7 rule.
Yeah, but the thing is, it's kind of a conditional thing.
Alright.
For this, you need to use the standard deviation of y given an x value instead of sy. So you probably would have used sy to answer the question, but technically you're supposed to use this guy because you're given an x value and you want to find the corresponding y value. And the formula for y given x is actually the original guy, but it's slightly altered by the r value. So here, instead of using this sy, you would use that. And so here you do that. The standard deviation of y given x would just be 18 times the radical of 1 minus 0.722 squared, which is what?
722 square minus that.
What? 12?
Times 18.
12.45?
Yeah.
Yeah, so you'll use this as the standard deviation of the y value.
And then you multiply that times 2 and add
Right,
2.
and then you multiply that by 2, you get 24, 25-ish. And then use that to determine. So, part C.
So it's 198.5, and it says.
So part C says, if a male who's more than 2 standard deviations above the mean weight for his height, he's considered obese. Is a male 68 inches weighing 200 pounds considered obese?
This was on the homework. I remember doing a problem like this, and I don't. It was? Oh, remember that extra problem I did, number 6? And then
Right,
I
so we know
I
that
could do it using 6, but then I
this is C. So we know that the average weight,
That's the problem. Because I remember doing
the average weight in this case for 68 inches, we actually compute that in part B, that was 173.6, right? If you take 2 times sy given x, what would you get?
You get 24.908. Wow.
And so now, if you take 173.6 plus 24.908, what would you get?
198.508.
198.5, right? Which is actually less than 200 pounds. So the guy is obese.
Can you do question 6?
From the same one, spring 09.
Are you gonna ask us this? I don't know.
So is the man obese? Oh, yeah, here.
Yes.
So,
The trick was if I gave you the x value in the beginning, which we know now is 68, then your standard deviation of y can be altered a little bit. Because your regression line isn't a perfect match, so they have to do this little fiddling with it to make it more accurate. Okay, in a discount supermarket, it's found that 60% of the sales are for less than $40. Find the probability of the following events. 3 randomly selected sales are each for less than 40. So here I know that the probability of less than 40 is 0.6. 8.
Isn't it just 0.6 times 0.6 times 0.6?
Yeah, so you walk through the store, you pick up 3 random items. What is the probability that they're all for less than $40? That makes it independent. The items are independent. So you want the probability that the first is less than 40 and the second is less than 40 and the third is less than 40. But these are all independent, so it's just the multiplication of all these guys. And for each one, the probability of being less than 40 is 0.6. So again, this goes back to trying to rephrase what you're asked for using the words and or, right? To get 3 things that are less than 40, you need the first and the second and the third, right? And we have independence here, and so we can multiply them. And so it's just 0.6 cubed, whatever that is. B. At least one of the randomly selected sales is for less than 40, right?
So you can get none of the randomly selected sales.
Yeah, do one or, that means because there are many options, right? The first could be less than 40 but not the other 2, or the second but not these 2, or the third but not these 2. Or you can have 2 who are less than 40 but not the third, or these 2 are less than 40 but not that one, or these 2 are less than 40 but not that one. There are too many ways to do it, so you kind of do the opposite. Use complements. The probability of at least one less than 40 is 1 minus the probability that none are less than 40. And there's literally only one way for that to happen. This is just 1 minus the probability that all are greater than 40.
Which is 40.4.
Right? What's the probability of being greater than 40?
0.4.
So it's going to be 0.4, so the opposite of that. But that 0.4 has to happen 3 times in a row. You pick those 3 elements and they're all greater. And so that would be what number?
0.936.
936.
So you have a good chance if you pick up 3 random items, at least one will be less than $40. You have a 93.6% chance. Now C, I didn't assign that because we actually need what I told you about just before this. You actually need that binomial form. So technically it's outside of our scope at the moment. The good thing, well, the thing is, now that you reread the question, can you see that it was binomial? Right? Because now we're picking out 11 randomly selected things, right? So you're repeating an experiment. You pick something up, put it in your shopping cart, do it again, do it again, do it again. Now there are 2 options. It's either less than $40 or not, right? And they're all independent. Like this, the price of this thing has nothing to do with the price of the thing on the other side of the store, right? So I have independence, only 2 outcomes, and I'm doing the same thing over and over. It gives me a binomial, and I use that formula that I gave you guys before to do it. But you don't need it for this test, so we'll skip that. Other questions?
Can you go over number 6 in fall 2010?
Here.
Part 1 and 2.
I think it was part 2. Is there one with a negative?
Also in 10.
Yeah, Paul.
Yeah. Part 2. It's
Okay, so according to the 1990 census, there are 122 million males in the US population and 128 million females. Based on these figures, what's the probability that a random selected person is male? So, we know the total population is What's the total population? 250 million, right? I know how many men there are. There are 122 million. I know how many women there are. There's 128 million. This means the probability of randomly selecting a male is 122 million out of 250 million. The millions would cancel. It's 122 out of 250. That reduces, but I don't really care to know what it reduces to. So that would be your answer for part A. So part A says, what is the probability that a random selected person is male? That's the probability. B. Among persons aged 65 and over, there are 67 males for every 100 females. Based on this, what is the probability that a randomly selected person over 65 is male? One thing that you should realize here, it's actually conditional. All right, so I'm not looking at the whole population anymore. I put a condition on it. I'm only looking at the people who are over 65. So basically what they're asking for here is we want the probability that a randomly selected person over 65 is male. So it means we already selected someone who's over 65. I want to know what's the probability that that person is a male. But I know that there are 67 for every 100 females. So this is going to be 67 over 167.
That's you.
And now C asks, are age and gender independent? Are they?
Yes.
How do you know?
Because you can be 67 and no, never mind. I just do.
Remember the Monty Python problem? Intuition can take you only so far. How do we know if something is independent?
Is it Monty Python?
There are two ways, right?
Yeah.
The Monty Hall problem. There are two ways, right? If the probability of A, B is the product,
Yeah.
we know it is independent. Or you can check that the probability of A given B is just the probability of A.
Oh.
Right? Now, we sort of have that situation, right? If I call being male A, being over 65 B, then it means I have probability of A given B, and I also have the probability of A. So if gender, age
Thank you.
were independent, then the probability of being male, given that you're over 65, must be equal to the probability of just being male, because it shouldn't matter what your age is and your gender.
That's not the case.
But this guy is equal to 122 over 250. And this guy is equal to 67 over 167. I don't think those two are equal. So they're not independent. Other questions? Huh? On the same one, fall 2010? So it's fall 2010 and problem 8. It says a polling organization claims that 15% of New Yorkers favor returning to a free tuition policy at CUNY. 15%.
It's not
A free education, that's definitely not, 85%. Disagree. I don't know, this sounds biased.
I think the gender one was pretty biased too.
Assuming that were the case, and a random sample of 2,500 New Yorkers are surveyed, what would you expect the number who support the proposal?
How many people were surveyed?
2,500.
2,500. So 15 minus 100 is 85.85 times that number.
Yeah, probability of being in favor is 0.15. So you expect 15% of people. So for 2,500 people, we expect 15% of them to be in favor.
And Republicans.
And Republican. So this is just 0.15 times 2,500, which is
375.
375.
Yeah.
All right, so we expect, so that's the expected number of people we expect to actually be in favor of this. Assuming the claim stated in 8A, what would be the probability that fewer than 13%?
Oh, no, Democrats, because they're in favor.
Oh, it was just B.
Yeah.
Oh, B, by the way, is also binomial. So after we do chapter 13, you should be able to figure that out, right? Because it's independent, you're repeating the same trial, you're giving someone a poll for them to take yes or no, and there are two outcomes. They either support it or they don't. So B would be binomial, and you'd use the formula that I gave you, where you take your probability of success, your P, to be 0.15, your Q would be 0.85, your N is 2,500, and then finding 30% of this, that would give you your K. And you use that formula. Other questions?
That's it for today.
No?
Shut up.
What? Which one?
Number 10.
On the same? Nah, forget that. We also have a theorem for that, by the way. Like I wrote it down. How scaling affects the correlation coefficient and all that. I'm not gonna ask anything like that.
What number?
Fall 2010, number 10.
Why?
Because if you memorize the theorem, it's way too easy. You don't need calculations for it or anything.
What kind of bonus are you gonna ask?
Have you made the test already?
Nope.
Yeah, you did. You told me you did.
I have my joking face on.
No, I remember.
You don't have a joking face.
I have a
It's on
joking
one-
face.
You have one face. and
Just
it's
like I told you guys,
Exactly
you know,
what I said.
I said the test was today, I said it with my joking face. You guys should have been paying attention. Other questions? Can probably get a couple more.
Go home.
Yeah?
Fall 2008.
Do I have that here?
I'm gonna go downstairs and print out that so I too can feel like a good student.
I don't think I followed it.
No, he does.
Fall 2008, number 4.
And 11.
He annotated them too. At least I got nothing.
Fall 8, number 4.
Who's
So
the
we're
top?
given 5 points. 1, 2, 4, 1. 5 minus 4. 3, 2. And 8. Find Sx, Sy, R.
Oh,
and
give us a problem like this.
the regression line. And it says use 3 decimal places rounding.
accountant's problem.
I love
It's a what?
An accountant problem. You just sit there with a calculator for a good 10 minutes.
Yeah. Well, I'll expect you to write out the formula.
Of course.
Ooh.
Okay, so you sort of name these guys like x1, y1, x2, y2, x3, y3, x4, y4, x5, y5, and then you go through these guys. So first we need to actually compute what?
standard deviation.
And the
On
mean.
mean.
Right, so we need x bar, we need y bar, and we need, we use those to find the standard deviation.
It's 2.4.
So this is just 1 plus 4 plus 5 plus 2 plus 0
10
over
divided by
5.
5 is 2.
Huh?
The first one is
2.5.
12 divided by 5.
1,
12
4,
divided by
5, 2, 0.
Yeah.
12
Yeah.
divided by 5.
Okay, so what is that?
I have no idea.
2.4.
Okay, and the y values, I take 2 plus 1 minus 4 plus 2 plus 8, and I divide that by 5.
1.8.
1.8. So now if I find the standard deviation of x, what is that?
X1.
It's all of this over 4.
1 minus 2.4 squared
1 minus 2.4 squared
plus 4 minus
4
2.4.
minus 2.4 squared plus
5 minus 2.4 squared.
Look at our class teamwork. How cute.
0 minus 2.4 squared.
yeah.
Over 5 minus 1. Which you already know.
Squared.
And that becomes
You
Who knows?
get 2.074.
SY is going to be very similar, except you use 1.8 as these values.
4.26.
4.26, similar to above. So I'll expect you to write this out, and then you can just, I don't know, put it in your calculator. And yeah, to find R, we need to do CXY and divide by the product of these two, so we need CXY. So it's 1 minus 2.4 times
4
2 minus 1.8 plus
4 minus 2.4 times 1 minus 1.8
plus dot dot dot. The last one would be
0 minus 2.4.
0 minus 2.4
8 minus 1.8.
times 8 minus 1.8. All of that over 4.
You get negative 7.9.
Negative 7.9. And so then we find R, which would be CXY divided by SXSY minus 7.9 divided by 2.074 times 4.26, which is
Negative 0.893.
0.893. So there's a pretty strong negative correlation here. And so the scatter plot should fit relatively close to a line of negative slope. And so now how do you find the regression line?
Well,
First, you need to find the slope of the regression line,
which you did.
B, which is
Negative
R times SY over SX minus 893, 4.26 over 2.074, which is
Negative 1.837.
1.837.
Not sure on this.
And then we use y minus y1 equals mx minus x1.
Oh, yes, it is.
Y minus y1 is y bar.
1.8.
M is the slope, which I just found here. X minus x bar, 2.4. And then just move this 1.8 over, and that's your regression line.
But to do the next part, we actually need the line, right?
Yeah, for part B, you literally just plug in x equals 3 into that and solve for y.
Okay.
So after doing all this, the part B is easy. And what did you guys say, number 11? Okay, so that's the blood type.
Don't you just multiply them together? Like the blood type and the factor, the transcription?
Same fall 08, problem 11. Okay, so we know that probability of A, probability of B, probability of AB, probability of O. Probability of blood type O is 0.43. There's a 0.41 chance you have blood type A, 0.11 chance here, 0.05. And we know that probability of RH plus, probability of RH minus is 0.86, 0.4. Okay. So now A says, what's the probability, to 2 decimal places, what's the probability that a randomly selected individual can be a donor for a person of type O positive? And we are only assuming what they told us up here. A person may receive blood from another person with the same RH factor and with the same type or type O. That's our only assumption. Okay. So A, probability donor for O positive. This is probability of O and RH plus, which they're independent, you just multiply them. Probably being an O is 0.43. Probably being RH plus 0.86. And whatever that is, 0.3 something. 0.03 something. 3698. Did I give you part B? No, I didn't. But hey, it's binomial.
Wow.
Right, so B is binomial. You're repeating an experiment 10 times. You want 3 or more successes.
Oh, I'm sorry, is this over already? That don't you have to find the probability of the same type?
Yeah, it was O and RH. O was the type we were looking for. Only an O can donate to an O.
Oh, okay.
Yeah. If it was another blood type, like we're looking for A, then I have to do A or O.
I thought it's another.
Yeah, no, it's O that we're looking for, so there was only one option. Yeah, part B would be binomial.
Oh, we're done.
So, in case you want to practice part B, you look at it as binomial. What you want is the probability of x greater than or equal to 3. Your probability of success P would be the probability of being B minus or O minus. Your Q would just be 1 minus N. Your N is going to be 10. This is your K value. And you'd actually use a complement. So I would use 1 minus the probability that your x is less than 3. So you'll only have to do 2 computations. Well, 0, 3 combinations, or 1, or 2, right? Instead of doing 3 or more, which you'd have to do 3, 4, 5, 6, 7, 8, 9, 10, you'd have to do 7 combinations. You can just do the complement and do 3. And for each of these, you're using that formula I gave you. N choose R, P to the R, Q to the N minus R. And this is the R value. Okay. You go in my random folder of papers.
No, I think
All right.
watching Jhevon's evil
We'll
laugh
see.
at the end was worth it. It was worth a few seconds of tears.